Today, we are directing our scientific inquiry to a region of the northern sky that is, by all accounts, quite unassuming, the constellation Leo Minor. Now, on the surface, it might appear as little more than a faint scattering of stars, but our objective today is to look past that apparent simplicity and uncover the really quite profound historical anomalies and astrophysical wonders it holds. This sentiment really captures the essence of our investigation today. You see, in astronomy, as in so many fields of science, it's often the quiet, overlooked subjects, the ones that exist in the shadow of cosmic giants like Ursa Major and Leo, that end up yielding the most remarkable and unexpected discoveries. So, here is our plan of attack. We will begin by establishing its position in the sky, then we'll investigate a very peculiar nominal paradox. From there, we'll explore the physics behind the echo of a dead quasar, delve into the constellation's historical origins, and we will conclude with a practical guide for observing it yourself. Let's get started. All right, first things first. To properly understand any celestial object, we must first establish its context. Where is it, and what are its fundamental properties? Let's examine the profile of Leo Minor. Okay, let's look at the hard data. And what it tells us is that by every conceivable metric, Leo Minor is, well, it's modest. It covers a mere 232 square degrees of the sky, which ranks it a rather lowly 64th out of the 88 official constellations. Even under perfect viewing conditions, you'd only be able to spot about 34 of its stars with the naked eye. And with its brightest stars shining at a faint magnitude of 3.8, it truly is just a quiet, sparse patch of sky. So, finding Leo Minor becomes an exercise in celestial navigation, using its far more prominent neighbors as signposts. It's a pattern so faint that you really can only find it by first anchoring your view on the giants that flank it. Let's trace that path on the sky together. First, you find the Big Dipper, which is, of course, part of Ursa Major. It's unmistakable. From there, your eye travels downwards until you locate the sickle, that backward question mark of stars that forms the mane and head of Leo the lion. Now, here's the key. You must then deliberately focus your attention on that dark, seemingly empty void between these two titans. It is only within that darkness that the faint stars of Leo Minor will begin to resolve into a shallow, elongated triangle. Now we shift our focus from its physical location to its nomenclature, and it's here that we encounter our first real puzzle, a strange and permanent error in astronomical cataloging that makes Leo Minor absolutely unique among all the constellations in the sky. So what's going on here? Well, it's a direct violation of a system that's been in place for centuries. The Bayer designation system is a simple, elegant hierarchy. Alpha is the brightest star, beta is the second brightest, and so on down the Greek alphabet. But in Leo Minor, that fundamental rule is broken. There is a beta star, but there is no alpha. From a cataloging perspective, the constellation is, well, it's headless. And this paradox is made all the more fascinating by its brightest star, the orange giant known as 46 LMI. You see, its proper name is Praecipua, which in Latin literally means the chief or the principal one. This is a profound irony, given that the chief star lacks the primary designation it's owed. This was simply an oversight by the 19th century astronomer Francis Baily, a human error now permanently etched into our celestial maps. Now, beyond this naming curiosity, Leo Minor does contain other objects of genuine scientific interest. Beta LMI is a classic binary system, a yellow giant and a white-yellow dwarf orbiting one another. But perhaps more compelling for modern astronomy is 20 LMI. At a distance of only 49 light-years, this binary star system is startlingly similar to our own Sun, which makes it an incredibly high-priority target in our ongoing search for Earth-like exoplanets. We now move beyond the visible stars into the deep sky phenomena hidden within the constellation's borders, and it is here, in the deep dark, that Leo Minor reveals its true and profound importance to modern astrophysics. Let's visualize this process. I want you to picture the core of the galaxy IC 2497, but as it was more than 200,000 years ago. At its center, a quasar, a supermassive black hole feeding on galactic matter, is blazing with unimaginable luminosity. Now imagine this quasar lets out a colossal pulse of high-energy radiation, a shell of light that expands outwards through space. Millennia pass. That shell of light finally slams into a massive, cold cloud of interstellar gas floating far from the galaxy. Fast forward to today. The quasar, the engine at the heart of the galaxy, has run out of fuel. It's gone dark, it is dead. but the light it emitted all that time ago is still traveling. The eerie green glow we see today, what we call Hanny's Voorwerp, is that gas cloud fluorescing as that ancient wave of radiation passes through it. We are literally witnessing an ionization echo, the ghost of a light source that no longer exists. And the story of its discovery is, in its own way, just as remarkable as the object itself. This phenomenon, one of the rarest of its kind in the known universe, was not found by a professional astronomer at a major observatory. It was identified by Hanny van Arkel, a schoolteacher from the Netherlands, who was volunteering for the Galaxy Zoo Citizen Science Project. It's an incredible testament to the power of public collaboration in scientific discovery. Also lurking within Leo Minor's boundaries is ARP 107. Now, I don't want you to picture a violent collision. This is something far more graceful. It is a gravitational ballet, unfolding over millions and millions of years. The two galaxies are in the slow process of merging, and their mutual gravitational attraction has pulled out this long, luminous bridge of stars and interstellar gas that now connects them. So, having examined its physics and deep sky objects, we now turn to its history. How did this faint, unassuming pattern of stars become an officially recognized constellation in the first place? The answer doesn't lie in ancient mythology, but rather in the meticulous work of a 17th century celestial cartographer. The historical sequence is quite clear. For thousands of years, this region of the sky was simply unformed space, informis, as it was called. It was a blank on the map. Then, in 1690, the Polish astronomer Johannes Hevelius, driven to fill in the gaps, officially delineated and named Leo Minor in his Great Star Atlas. And finally, in the 19th century, Francis Baily's cataloging work cemented its modern identity, complete with its now famous error. Hevelius's logic was purely that of a cartographer. He was driven to create a complete and orderly map of the heavens. His reasoning was thematic. It made sense to him to place a small lion, a lion cub, right next to the great lion, Leo, and in proximity to the great bear, Ursa Major. As the attributed quote suggests, for Hevelius it was simply a matter of proper celestial organization. And finally, let's bring all of this theoretical and historical discussion into the practical realm. After all this, how can you go out and find these objects for yourself? Here is your checklist. To find it, you want to locate that patch of sky situated directly above the back of Leo the lion. Now, if you're observing from a light-polluted urban area, your only realistic naked eye target is going to be 46 LMI, Praecipua itself. And for your best chance, plan your observation for the spring months, March and April, when the constellation is highest in the northern night sky. And if you have access to a small telescope, your primary target in this region should absolutely be the galaxy NGC 3344. It is a spectacular specimen of a spiral galaxy, and it happens to be oriented perfectly face-on from our vantage point, which allows for a breathtakingly clear view of its grand spiral structure. So, to summarize, the story of Leo Minor is really a perfect microcosm of scientific progress. It starts as a cartographer's solution to a blank space, it's defined by a simple cataloging error, and it ultimately becomes the site of a profound astrophysical discovery made not by a professional, but by an engaged citizen. Its true significance is not found in its brightness, but in the secrets it was hiding. And this leaves us with a final and, I think, essential question. What Leo Minor demonstrates is that cosmic importance is not a function of apparent magnitude. It forces us to ask, what other profound truths, what other echoes of the ancient universe are waiting to be found not in the brilliant galactic cores or famous nebulae, but in the quietest, darkest, and most overlooked corners of our universe?